Hi, my name is Arnav, and I will be showing my project for my AML promo course about comparison of UNO versus traditional solvers for the Navier-Stokes equation, particularly in this case, the Darcy flow equation, right? Getting right into it, we will get into the problem statement. Um, I apologize for the late exam. Some certain things could not load in the inline text, even with uh, all the methods available. So, our problem statement is we want to learn the solution operator for the 2D Darcy flow equation and compare if after learning, when we solve such Darcy flow equation or any differential equation, if it's actually good enough to be a alternative to the regular ab initio methods that exist uh, in uh, uh, the industry. So naturally, it starts with an input, some 2D diffusion constant, a field of some a heat map of sorts. This represents the material itself, as you can see the permeability of the material. This is because, as I said, the Darcy flow equation is a porous medium version of the Navier-Stokes equation. So while Navier-Stokes normally is in a continuous medium, this one we're going to take a very specific porous diffusion field in which we will actually be running these uh, calculations. Now we then have a function that acts as the pressure. This is the actual delta, the change in entropy that we want to see. And then we try to find the solution. Very straightforward. It's almost the same as predicting if a rock falls from a high place. We have gravity. We try to see how fast it goes. Either we literally calculate the velocity via Newtonian mechanics, or we see multiple rocks falling many times and we instantly predict how fast the rock will fall without having to calculate it per use case. However, the training itself will be long. So, but that assumption, the guess, is it good enough that off the trail? That's what we're going to check in this project. So, generated thousands of pairs in the digital solver. This is the equivalent of generating loads of data for the UNO to train on. But we know this for a fact is perfectly accurate, right? And then we're just going to compare if post learning on this, when the UNO actually tries to uh, guess on random new data, will it actually work or not? Within obviously certain constraints, we have in this project not changed the fundamental mapping. So the fundamental diffusion coefficients that been given and the pressure is the same. This is technically not ideal, but we're just simply trying to find out that if the UNO learns within a certain amount of data, will it work on the same kind of data as well, right? So now, the big picture. So we just want to understand first what is a UNO, right? UNO or a U-shaped neural operator, and neural operators like this one, like the FNO, which is Fourier neural operator, is essentially a um, a method with which I can train the certain operators required in every differential equation uh, and then for that certain case, and then run those operators itself to solve the question. For example, if I have a differential operator, right, and I know that dou y of dou x is equal to something, I need to solve the differential equation. if I simply see loads of differential equations and feed it into a differential operator will learn, oh, this is how I solve the differential equation. And eventually, I can instantly just put in an input. It'll know how to do the output based on the differentiation, and it'll give me the differential. I can do this for a Laplacian, I can do this for a Hamiltonian, and it has, because I can do it for different kinds of operators, I can mix and match and make it more useful for multiple more complex problems, which have maybe heat flow and fluid dynamics and electrodynamics and what. So it's an extremely useful tool that's in our toolbox right now. And so we'll see how effective it actually is. This is the index it will be given just now. This V naught X is simply a theta phase change on the input dimensions. Uh, four equations. Um, this is showing the Darcy flow equation. First, I want to show the Darcy flow equation that we actually have. It's just the del divergence of the uh, multiplied by the actual dimension within which we are existing. In times the dimension, the gradient of the pressure itself. That's what Vx is here, the pressure. Yeah. And that equates to the amount of sources. This is directly uh, coming from uh, fluid. So now back to the UNO. Uh, what is an integral operator, right? So fundamentally, the way a UNO works, a UNO is actually simply a couple of blocks and like a set of FNs together. And in this case, the architecture is what makes the main difference, and how we use that architecture is the key point. Over here, uh, essentially, we're gonna first downsample and then we're gonna upsample, right? As we can see. Again, I apologize for the latex. So essentially, first it takes the entire image, then it downsamples it, makes it a smaller image, so it's able to see the broad global patterns, as it's written over here, right? Patterns that we can, from a bird's eye perspective, post which it will upsample and then look at the nitty-gritty details within those small um, patterns that they saw, essentially. So this process of downsampling, then upsampling, makes sure that it does not hallucinate, that they tends to do, and not be narrow fielded at one certain location, while also making sure that they have a good eye for detail in seeing what the similarities are or to learn about certain publishers within the data. Told you I say because of this Darcy flow, but otherwise it would. So again, this is the way that the sample works. Um, the U of X is again our pressure field multiplied by our theta coefficient. This function changes based on the heat map that is again iterated over the input field. So we can see input of one channel that flows up to 60 million. So we are compressing. This is the compression that's happening at the encoding, uh, putting down the pressure, and then decompressing. So the encoding that shrinks the resolution, then a decode just increasing the resolution, and then finally it sets out all the information that you got from that increased resolution multiple channels into one, right? The wide 64 channel workspace that we're trying to say is how it's able to deal with the increased resolution. But first, it obviously reduce the resolution. So that's essentially how it works. Uh, This is the architecture here. But fundamentally, it's just a bunch of Fourier layers. Again, in the U shape, the encoding side that expands it, decoding side that um, shrinks it. But each individual component is essentially a Fourier neural. Now, now that we have understood how the Fourier this works, again, the Fourier neural operator is obviously just the neural operator for a Fourier series. So it's going to learn how to change everything from time domain into a frequency domain. Right. So now back to the numerical solver. So now we're going to check how the numerical solver, which is the standard method, is solving uh, the Darcy flow equations in order to get the perfect solution, so to speak. Right. And it uses this thing called finite difference, which is very similar to a Newton-Raphson method. But essentially, as you can see, this formula approximates the 2D Laplacian at the grid point by looking only at its four closest names, which is the XYZ, those are top down, side, side. And based on that average at small intervals, we're able to find out how much um, the, I mean, we're trying to figure out the gradients and the secondary gradients of every point of uh, the Darcy field, every point in the input field and the gradients of the pressure itself. Once we find set gradients, we can then approximate how the rest of the equation is going to carry out. So it's essentially trying to simulate calculus, um, you know, small um, iterations within a curve will become a straight line. Then I assume the gradient to be whatever the straight line is, and then I calculate it. So this is our PDE normally. Then we're averaging it out based on these very small edges that we are assuming is small enough that there's no actual second degree curvature there. It's only one straight line. And then based on this simple algebra, I then push forward. So then iterated these sides, right? So um so this loop, yeah. So this loop ran for a max iterations of 5,000 times. This is specifically for my particular question, my particular problem statement, and this is the so this is I'm talking about particularly with what we did. Um, for example, the generate data.py is the file that I have used. You will show uh, that has ran the Jacobi solver in order to produce all the data that we need for the UNO to read upon. So now let's see uh, how we can start comparing this, right? So the classical solver, as I said, does not train, it's purely deterministic, and it just executes a set of multiplications. Um, Naturally, exactly like the rock analogy, we drop a rock, we try to use Newtonian mechanics to solve what the velocity will be, where will it be at a certain period of time, etc. Whereas you do not need to do this with the unit, right? So whenever you input a new input field, it must start from zero and it will keep iterating. Again, Newton-Raphson method, it simply iterates until it converges. Naturally, this 5,000 iterators is just an approximation. It so happens to be that for Dawson we use this, but it can be more, can be less, but it tends to be more. Because this specific um, problem does not have a very complicated A of X field. It was a simple uh, linear, like more homogeneous mixture. Now, the UNO. So, here I'm going to look at the problems and answers here. So I'm going to look at the input and the output. Then I'm going to train the model based on whatever I see. Then I'm going to learn a pattern. One time I'm going to learn the pattern, then it understood it. Then after this, every single time it's going to try to approximate and predict what, for any given input, what the output can be. Right? Naturally, you see this as a 0.42 milliseconds, or this is 200 milliseconds. This is for 5,000 uh, iterative loops. In our model, we actually saw a almost 147 times increase in speed. Oh, this is 147. Okay. So yeah, an extremely high resistance, which we will see, right? Um, so uh, now pros and cons. Right? The classical solver can never be wrong for the most part. While it is converging to a correct solution, if you let it go for enough number of times, it will converge to the solution required. There will never be an issue, right? However, it's extremely slow. So it's perfect, but it's slow. Whereas naturally in the UNO, 470 times faster, but there is a little bit of an error, right? And naturally, there is a huge upfront cost of training the model, but if the error is not too high, then many a times the speed is worth the effort required for training the model, right? So the real question that we need to ask is how bad is the L2 error? If the L2 error is, in this case, it's 1.49 times 10 to the power minus 4, which is extremely close, right? If it maintains these kind of numbers, then it's perfectly viable for most use cases. If it does not, that's where there's an issue. So where the threshold lies for enough error management, where I can have a trade-off where the error is high, but my time is low. So my trade-off, essentially. If in this case we see that the error is low enough, we can then consider UNOs to be a viable solution for solving, at least in this case, fluid dynamics questions. And fluid dynamics tends to be one of the most complicated ones to solve when it gets, I mean, computation intensive ones to solve when it gets critical. So let's see how it is, how we're doing this. So again, this project, again, the core question is solving PDEs like the Darcy flow and which Richter solvers is slow. The hypothesis is UNOs can approximate it fairly well, but the speed is what we and we want to see how much the speed gain is. That's what we're going to be checking, and how much the error is. These are the two things that we want to check. If the speed gain is high and the error is low, that is perfect. If not, how much are we allowing to let go? And if it's okay for our city. So this is how our project was made. First, I used a generate data.py um, uh, file that helps taking multiple input values that was randomly generated and then finally creates our output. This was run multiple times and then we generate the data set from this, which I named as Darcy data.mpz. Uh, Post which now the UNO model is going to use this Darcy data that we have, which is has the input and the outputs, and then learn based off this. Uh, Now the script um, gave us a set of measurements to process 1000 samples. As we can see, these are just the metrics that I've used and gave the traditional solver time, right? Now for the UL. Um, so this particular repository uh, has been taken from uh, a certain from the neural operator repository, and he, this repo has used the neural operator repository. We have used the architecture of UNO9 from the official repository, and then try to run, right? Um, After using just the UNO9 architecture, we now have to check based on the output, uh, the error, and the time, right? Post running it for, in this case, we did 100 epochs. Uh, we have found that the training loss, the error, L2 error was 1.49 in 10 to the power minus 4, as I mentioned in the previous slide. And the average time per sample is 0.42 milliseconds, which is extremely fast, which is exactly what we want. And our error is extremely less, which is again exactly what 99.985. So now let's make some inferences. First, should see how the code is running. So we can see here we have uh, the results, the train UNO dot py and for results. After running Python train UNO dot py, we get the results that I have already shown. Um, and actually, I also saved it on the output, which is this. This is exactly how it looks. Uh, this is the time spent and the relative error and the test error. So the train relative L2 error, while it was training on the same data set, and a test data set. Actually, we have to check on different data sets. Right? This is run for 100 epochs. Yeah, for the time switch. This is the average path size is 0.6, average time plus convenience. So that's how we see this works. Um, yeah. So now going back to the slide, we'll get to the code if needed. Um, so we now can make some inferences um, based on this plot. And the first inference we get to make is uh, we compare, we want to compare the time. One was 200 milliseconds, one was 0.42 milliseconds, so 470 times faster. Shortly, we see that the UNO is a lot faster and perfectly used. Um, Secondly, the accuracy, 1.49, is for extremely small error, and that's good. So from this, we can see that the UNO is indeed a extremely viable source, extremely viable alternative to the numerical software. Just as a point of view, should tell you that over here, originally, you have to first generate the data.py. After generating the data.py, I've used this darcy data.lpz file. Uh, After running the darcy data.lpz file and parsing it into train UNO model, I got the entire data, and then I have plot results, right? So this was the essential thing. All these other files are from the neural operator library, which is the standard library for this. So now let's see some of the data that we have obtained from the plot results, right? So this is the ground truth pressure, the UNO production pressure, and the absolute. This input permeability field is not the random input. This is the A of X, which means that the field is homogeneous. That's all that is, right? There is a random input that has been provided, uh, but I did not. So now we see that this is the absolute error, which is quite close to zero. Um, yeah. So now you can see, first of all, the input permeability. What was this? This was just A of X that we had seen earlier, right? Then we have ground truth. This is from our generate data.py. I iteratively solve the Jacobi solver with numerical solver and get each of the solutions for all of the random inputs through A of X, which ran to this equation right here. Yes, sorry, this equation right here. Yeah. Then we post generating it. That's when I got the Darcy flow data.npz file, right? Then post that we have a panel tree which linear prediction of the pressure, right? This was the second data, lunar prediction. This was the Jacobi prediction. And then we do L2 error, which is just subtracting the predictions. So this is another graphical way that we can see how nicely this worked out. And as we can see, even by eyeballing it, it looks pretty simple, right? So that's there. Uh, so conclusions. We successfully trained the UNO model uh, for the Darcy flow. UNO model is exceptionally accurate. It was exceptionally faster, and the trade-off was extremely slight in terms of how much we are actually losing out on accuracy. So, in conclusion, we would like, which we were trying to find out essentially, can we use UNOs as a viable and powerful tool for accelerating scientific computing, right? And as we can see by this specific example, we indeed can. So this was the latest again. Thanks. Sorry about that. And thank you for listening.